Let's go. This is the title of my presentation, as already introduced, and why we need metamaterials. Metamaterials offer some advices, like a possibility to obtain an hyper resolution, and so to go beyond the classical optical resolution, achieving very high value in terms of resolution. Indeed, at the end of this presentation, I will show you how it's possible to reduce a beam size of a photopolymerized voxel at least of 90% to the state of art. So, as you can read on this previous slide, you can see that it is possible to go beyond metamaterials thanks to this, go beyond materials thanks to the metamaterials, a very particular family of humankind materials that offers a possibility to exploit very fancy properties. So we need just to introduce the main aspects about metamaterials, their isofrequencies. They possess isofrequencies that change as a function of the electric constant value and sign. And so if we exploit these, as you well know, it's possible to modify the properties until achieving a possibility to open new particular scenarios, such as the guided modes between metal barriers when we sandwiches a system like metal, insulator, and so on, or just if we stop using a system composed by three layers like metal, insulator, metal. So this is just the main aspects that we have to know if we want to start to prototype some particular systems. Indeed, using just a numerical ellipsometer analysis that me and my colleagues presented in this work, is possible to design a particular system like these cavities that open in the visible range one or more than one spectral features, like this dip in reflectance or peak in transmittance, and such modifications, such particular features such sigmoidal shape in the psi and delta ellipsometer parameters. These open the possibility to fabricate materials that shift their electromagnetic wave responses and resonances, and just using the modified effective medium theory to take in account more than two materials and the different dielectric thickness, is possible to evaluate the resonances thanks to this dielectric map that show the reflectance, transmittance, or absorbance as we want to evaluate using a transfer matrix method, and just varying the dielectric layer. So when we vary the dielectric layer, we can obtain these different resonances as represented and reported in this slide. You can see that if we use an ITO layer of 65 nanometers, we have a resonance frequencies close to 460 nanometers, and if we use the 85 nanometers of IO2, we have a resonances in the 30 nanometers. That means that we are passing from blue to green. So this is represented by this study that we published on advanced optical materials that show that it's possible, just changing the viewing angle of this material, to see different colors that are reflected, transmitted, or absorbed. So, and this opens a possibility to realize a filter for wavelengths, or for example, just exploiting the delta as reported in the delta graph on the right, the giant dephasing that is possible to use for Gaussian shift effect. So it's possible to use it for sensing, exploiting the Gaussian shift effect. But if we want to introduce the two-photon direct laser writing, the process that we want to improve using metamaterials, I just want to spend a few words about what is two-photon direct laser writing process. This process is just a technique that uses a focalized beam to build a 3D structure using light and using a polymer that is active and polymerized when it's enlightened. The curing starts when the two photons are focalized in a point. So it starts, and at the end, as you can see in the first cartoon, we realize this got using the two-photon direct laser writing. And as it is presented by the two real images, A and B, taken from the nanoscribe company, it is possible to see that if we use the one photon absorber, we see the entire light cone. It means that we focalize and we cure polymer in the other part, not only where we are focalized. In the other case, panel B, we see just the point where we are focused. It means that we are able to write just one point. And it is represented by the image of the some hexagonal shape that are piled on layer by layer, and we can see the voxel cartoon that is overlapped just to realize, to fabricate this line of each elements. At the end, it is possible to realize some structure as represented by the State of Liberty, the Brandenburg Gate, and this Fresnel lens. When I saw that it's possible to produce optics using this process, I thought that, okay, we have to find a way to improve this resolution to produce meta lenses. And so, me and my research group found a way to realize these metamaterials that is a sandwich of silver, zinc oxide, silver, zinc oxide, where the first zinc oxide layer is a cavity that supports two modes. The 780 nanometers, that is the main wavelength where the two-photon direct laser writing setup that I used works, and 400 nanometers, that is if we want to try also the one photon absorption. So we took the classical system as already described for two-photon direct laser writing, and we covered the glass with these 4 layers. This opens a possibility to obtain this transmitted, reflected band at the two main wavelengths, at the resonance wavelengths. And just if you take a look to the simulation and experiment of the in both polarization for the reflectance and transmittance map as a function of the incident angle, we can see that there isn't a strong difference in angle. It means that we are able to collect whole k-wave vector that comes from the objective lens. So after that, we realized the sample, we used the two-photon direct laser writing, and we saw that if we compare the beam size through the glass to the MIMI, the reduction is close to the 40%, 20% for the 50 times and 10 times respectively beam objective lens magnification. But if we start to produce the first preliminary test that can be just a grating, we see that the height reduction, the width reduction is close to 89% and 50% respectively. It means that we are reducing the voxel size and we are able to go down in terms of beam of voxel size and go up to go at a higher level for the resolution. Indeed, after that, we propose to realize a nano portrait of this famous Lady with an Ermine of Leonardo da Vinci. We reproduced this at the nanoscale. If we think that it is just high, the total height of the portrait in 3D is 550 nanometers. 550 nanometers, and we collected the picture through the MIMI that exploits also a possibility to use it as a lens that collimates the light, and we can see in panel C the image of the lady on the glass, but we collected also the topography using an AFM, as in panel D, H, and the other one that show details and 3D view, but also using a confocal microscope due to the fact that the resin that we used is fluorescent. And we saw that we are able to collect different slices of this portrait, the silhouette on the bottom and the other details that stay on the eye, on the top of this portrait. And finally, we reconstructed, as reproduced in panel G, the entire structure. And it is possible to see that all details are contained also in the fluorescence map. And also the thickness is close to the AFM. It means that we are very able to increase the resolution of the two-photon direct laser writer. At the end, thanks to these results that we collected by the first preliminary test on the grating, the reproduction, and the possibility to draw all details such in a portrait but at the nanoscale, I used the machine learning algorithm to design a per meta lens that is able to focalize more than one wavelength, in that case 5 from UV to the end of the visible range. And thanks to this data, thanks to the numerical simulation, different approach that combined altogether offers a very wide scenario to realize metalenses, it was possible to realize metalenses through two-photon direct laser writing. And characterizing them, we denotated that using this optical setup for the characterization, that is a confocal microscope that is possible to customize, to introduce more than one wavelength at the same time, to obtain a white light that is a combination of the RGB using lasers, using an external lamp. We characterized the metalenses in terms of optics, and as reported here, in terms of AFM, we see that the total height of each ridge is 40 nanometers. The total width of each ridge is close to 300 nanometers. And we also demonstrate again that it's possible to exploit the self-collimation, self-canalization of the metamaterials that is underneath the metalenses, and we are able to, using a proper band filter, to recognize all details that are contained in the metalenses at the right resonant wavelength, and out of resonance we are not able to reconstruct the final picture. And characterizing these metalenses, we these ultra-flat metalenses, we want to underline that it is just 400 nanometers of thickness. That if we characterize this lens, this meta lens, using 405 nanometers, 532 nanometers, 633 nanometers, the free laser altogether, or a white lamp, it's possible to see that we have the same focus close to 1.12 millimeter, a depth of focus of some hundreds microns, and the full width of maximum that characterize each focal spot is close to 0.9 microns for single laser, and 1.5, 1.65 for the combination of the free laser and for the wave lamp, respectively. At the end, just to prove and to confirm that these metalenses are also free of any color aberration, we used a color gamut plot to show that if we enlighten metalenses with use a green laser that passes through the metalensis, the green is in the right position with the green on the gamut plot. The same story for the red, for the blue. But when we start to combine these, we see that it's possible to obtain a pure RGB close to the white lamp if we use a 445 instead of the 405 nanometers as the blue wavelength. And if we combine these or use the previous blue laser, we obtain the 3L indicated on this plot gamut. That means to obtain a warm white light instead of a cold white light. So this is the how to achieve hyper resolution using through to photon direct laser writing using or leveraging on metamaterials such as metal insulator stack. Just to remark that this presentation shows the tool that we developed that is the HAMED for to numerically predict the ellipsometer parameters, the fabrication and characterization of metamaterials with particular features such as the gap and surface plasmon polarity and generation, color use, plasmonic fingerprints related to pseudo dielectric function, and also strong light self-collimation and self-canalization. And the last but not least, leveraging on epsilon-near-zero metamaterials, as I said, it is possible to drastically increase the higher resolution in order to fabricate apochromatic metalenses, nanoportrait, or other stuff that we want to enrich of details at the nanoscale. Thank you for your kind attention. And for future collaboration or question, don't hesitate to contact me. Here there is my email.